if we want to compare translational versus rotational quantities, there's a lot of similarity. They have very similar structure to the formulas, the definitions, the equations, everything like that, just different meanings of some of the variables. Like for translational motion, if you want to make an object accelerate, what do you have to do to it?
Change its velocity and apply force.
The changing velocity is what the acceleration is. And I would say the force is how you make that happen. So you apply a force to make the object accelerate, which means the rate of change in velocity. And what's the constant of proportionality that links those together?
Mass.
The mass. More mass means it takes more force to get the same acceleration. Or more mass means you get less acceleration for the same amount of force. And the rotational version of this is exactly the same structure, except what variables do we use instead of, like what do we use instead of force when we're talking about rotational motion?
Torque?
Yeah, you apply a torque. And instead of translational acceleration, we're just going to have rotational acceleration, alpha, which represents how fast your rate of spin is changing, how fast your angular velocity is changing. And what's the constant of proportionality here? Instead of mass, what would we use?
Moment of inertia.
Yeah, I, the moment of inertia. And in both cases, that constant of proportionality represents a difficulty level. More mass means it takes more force to get the same translational acceleration. More moment of inertia means it takes more torque to get the same amount of rotational acceleration. So it really is just the level of difficulty for changing how it's moving. And there's a few other ways we can write this also. First, I want to emphasize one thing though. This equation only works if moment of inertia is constant. If the moment of inertia is changing, this equation is not exactly valid. And the reason we have to specify that in comparison to this one, which should just be always true, can the mass of an object change? Not really, no. I mean, it could like split out. Like let's say maybe you've got a rocket that's burning fuel. The rocket's mass, including the fuel inside it, is getting smaller and smaller because it's shooting some fuel out the back as exhaust. But in that case, it's not really that an object is getting less massive. It's that an object is splitting into several smaller objects. But the total mass of the whole system is still the same. So typically, we would not expect mass to change. But for moment of inertia, what does moment of inertia depend on? Moment of inertia is mass and what other information combined?
R squared?
Yeah, mass times radius squared, or something about a mass and a distance squared. It involves mass and position, where the mass is within the object. So a moment of inertia, even if the mass is staying constant, the moment of inertia could change if that mass is moving around inside the object. For example, let's say you've got a wheel with some spokes, and you've got some heavy masses towards the inner region. If this spins around, those masses are fairly close to the center, so they're not actually going to have much moment of inertia. But let's say as this spins, these masses slide along these tracks and get further out. If those masses have moved further outwards on the spokes, what happens to the moment of inertia? Yeah, the moment of inertia is going to change. If we take the simplest form of the equation, moment of inertia is mr squared, which isn't necessarily valid for complicated shapes, but for each one of these individual objects, each one of these little sliders, it is. The mass of that slider stays the same, but the radius has increased. It's gotten further from the pivot point at the center. So since r has increased, the moment of inertia also increases. In fact, it's going to be increasing pretty drastically because the r is being squared. So let's say you multiply r by 5, square that, you're actually multiplying the moment of inertia by 25. So moment of inertia changes pretty drastically if you increase or decrease the radius, how far the mass is from the center. And this shows up all the time in basically anything involving a spinning object. If you've got, like, let's say you are holding your arms outstretched and spinning. If you pull your arms in while you're spinning, what's going to happen?
The radius decreases, so inertia decreases.
Right. You've decreased the radius of some of the mass of your arms themselves. And this is even more pronounced if you're holding some sort of heavy weight in your arm, in your hand. If you're holding like a 20-pound bag of flour or something and you pull it inwards, you've taken all that mass and moved it to a closer location, a smaller radius. So that decreases your moment of inertia, which means this formula is not necessarily valid anymore because your moment of inertia is changing. So this really only applies to situations where the moment of inertia is not changing. Typically, if you've got a rigid object that's not changing its shape, not changing where the mass is within the object. But we can take a look at a couple other ways to look at this. For instance, what exactly is acceleration in the first place? What does acceleration mean? It's the second derivative of position. It would be the first derivative of velocity. Acceleration is the first derivative of velocity, which is the second derivative of position. So it's how quickly the velocity is changing, not just how much the velocity is changing, but how quickly the velocity is changing, the rate of change. So we could rewrite that as mass times change in velocity over change in time. And we can rearrange that a little bit. If we combine mass times change in velocity, what do we call mass times change in velocity? Right. So mass times velocity is momentum. Mass times change in velocity is change in momentum. So if we bundle those together, we get force equals derivative of momentum. The force, and I should really specify the net force in all of these, the total force acting on the object. The net force acting on the object, the total of all the forces added together, equals the derivative of momentum. So however much force there is, that tells you how fast the momentum is changing. It also tells you, since these are vectors, that the momentum is going to be changing in the direction that the force is being applied. And if there's no force, then there's no change in momentum. Momentum is going to be constant if there's no force acting on the object. Or for a larger system of several objects, the total momentum doesn't change if there's no external force acting on the system from somewhere else. So this is where we get the idea of conservation of momentum. Momentum stays constant if and only if the net force is zero. We could also rearrange this to solve for change in momentum by doing what? If you wanted to find the change in momentum, what would you have to do? Or alternatively, how do you undo a derivative?
Take the integral.
Right, we could take the integral of both sides and say momentum is the integral of force with respect to time. So in general, I guess I should really say the change in momentum from some initial time to some final time. The change in momentum is the integral of force. And if you have a force that's changing, then you'd have to have some formula for force in terms of time and integrate that. But in the simplest case, where force is constant, what's the integral of a constant? Integral of f if f is constant.
It's just x, right?
Well, in this case, it would be t because t is what we're integrating with respect to, but yeah. So just f times t. And that's evaluated from t initial to t final. So we'd plug in t final, plug in t initial, and subtract. T final minus t initial would just be delta t. So if the force is constant, we can use this idea of impulse, that the change in momentum is just the force times the amount of time it takes. More broadly, if the force is changing, impulse is found using this integral. But in general, if force is constant, then the impulse is just amount of force times how much time it takes, or how much time the force lasts. And that tells you how much the momentum changes. Any questions on that so far? So this idea of impulse is really just an alternate way of writing Newton's second law. Newton's first law is if there's no force, then there's no acceleration. Newton's second law is the amount of force equals mass, the total force on the object equals mass times acceleration. But rearrange the variables algebraically, and you get this idea of impulse, that the force times how much time it lasts, also known as the impulse, tells you how much the object's momentum changes as a result of that force. Any questions on that so far? If we try the same approach for rotational motion, how do we define angular acceleration, rotational acceleration? What does that alpha actually mean? When we say an object is rotationally accelerating, what's it doing as time passes? What's changing if the object is rotationally accelerating?
Angular velocity?
Yeah, the angular velocity. It's changing how fast it's spinning, or alternatively changing which direction it's at, which axis it's rotating around. But in general, angular acceleration is the derivative of omega, the derivative of the angular velocity. So angular acceleration tells you how fast the angular velocity changes as time passes. And that means we can go through this exact same approach. We can replace angular acceleration with this derivative. We can say torque equals moment of inertia times change in angular velocity over change in time. And then we can bundle these terms together, moment of inertia times change in angular velocity. This quantity we call rotational momentum. In the same way that mass times velocity was translational momentum, we call moment of inertia times angular velocity the rotational momentum. And this is actually the exact same sort of structure. If you take a look at how we define this, translational momentum we define as mass times velocity, translational velocity. Rotational momentum or angular momentum we define, and this is usually written as a capital L, which counts as a vector, is typically written as moment of inertia times angular velocity. And even though these formulas look different, they have the exact same structure. In both cases, we're saying there's something we call momentum that's equal to how fast the object is moving or spinning times the difficulty level of changing that move or spin. Because translational velocity and angular velocity both represent some sort of rate of change. How fast the position is changing versus how fast the orientation is changing. And mass and moment of inertia both represent difficulty levels. Mass is how difficult it is to change the velocity. Moment of inertia is how difficult it is to change the angular velocity. So these formulas, these definitions of angular momentum versus translational momentum, they have the exact same structure. They just have different meanings of the individual variables. But overall, they mean very similar things. They do have different units of measurement though, so they're not interchangeable. You can't just say one type of momentum changes into the other, or you can't add these together or subtract them because they have different units. So in this case, this is very unlike energy. Energy, for an example, you could have translational kinetic energy, you could have rotational kinetic energy. Those are both energies. Those are measured in joules. You can add them together to get the total energy. But translational momentum, what are the units of measurement for this?
Kilograms meters per second.
Yeah, kilograms times meters per second. And what about for rotational momentum? What's moment of inertia typically measured in?
Kilograms meters squared.
Yeah, because it's a mass times radius squared typically, or some fraction times mass times radius squared. And what about angular velocity? What's that measured in?
Like 1/seconds.
Right. That's 1/seconds. We usually think of it as radians per second, but radians is technically unitless, so it's really just 1/seconds. So these are not the same units of measurement. Translational momentum and rotational momentum are not interchangeable. There's no way to just add them together to get a total momentum because they're measuring different things. And they don't even have the same units of measurement. However, the units of measurement suggest there may be some way of converting between them. What would you have to multiply this by to turn it into this?
Like just the mass again?
Not mass in this case, because this m in the units doesn't represent mass. What does this m represent?
Meters, like radius maybe? Or
Yeah,
like
some sort of distance. So there may be some way of multiplying a translational momentum by a distance to get a rotational momentum. And whether that's possible or not depends on the situation. Whether an object is, like if an object is spinning in place, it has rotational momentum, but no translational momentum. If it's just drifting through space, it has translational momentum, but no rotational momentum. If it's drifting and gradually tumbling, then it may have translational and rotational momentum, but they don't have to be related to each other. But there are some circumstances where they are related. Like if you've got a wheel rolling along a surface, a wheel rolling along the ground, in that case, the faster it moves forward, the faster it spins. So there is a relationship between how fast it's moving forward versus how fast it's spinning around. So in cases like that, where the translational motion and rotational motion are linked together, there are ways to convert back and forth between these two. Alternatively, another example would be if you've got like an object, maybe you've got like a rock on a string that's spinning around. It's got translational momentum because it's moving through space, but it's also moving along a curved path, and so its angle is changing as time passes. That would mean it has both translational and rotational momentum, which are really talking about the same motion, just different ways of looking at it. So there are some cases where these can be converted back and forth between each other, but in many cases, they don't even have to be related at all because they are measuring different things. Any other questions on that so far? And if we want to take a look at a change here, we can use the idea of rotational impulse or angular impulse. If we go through the same sort of process here, looking at the rate of change, if you want to change the angular momentum, assuming the moment of inertia is not changing, then we just get moment of inertia times change in angular velocity. But what do you have to do to make that change happen? What do you have to apply to the object to make its angular velocity change?
torque?
Yeah, you've got to apply a torque. And this moment of inertia times change in angular velocity, that's almost moment of inertia times angular acceleration. All we really have to do is divide by delta time and also multiply by delta time to balance that out. What we now have here, moment of inertia times angular acceleration, that should be torque. So that means we can write change in angular momentum as torque times change in time. And here's the idea of angular impulse. And again, note that this is the exact same structure as translational impulse. To change the translational momentum, you apply a force for some amount of time. To change the angular momentum or rotational momentum, you apply a torque for some amount of time. And the amount of change equals how much torque times how much time it lasts. So again, exact same structure of the equation, just different meanings of the variables. Any other questions on that so far? And going back to the idea of conservation, when would you expect there to be no change in momentum?
No force, no
Right.
external force.
Yeah, if there's no external force acting on the system. So you get conservation of momentum. P total is conserved. P total doesn't change if there's no external force. Can you make a similar statement involving rotational motion using this idea?
I guess if there's no torque,
Mm-hmm.
and so there's no angular impulse.
What's the rotational version of momentum?
Just angular momentum, right?
Yeah. Angular momentum. So we can make a similar statement saying the total angular momentum doesn't change unless, what would you have to do to make the total angular momentum change?
Introduce torque.
Yeah, specifically an external torque. So the total angular momentum doesn't change if there's no external torque. And note that these are different statements. It's possible to have an external force that doesn't count as a torque. Like for instance, if you just have some object and you're pushing on the middle of it, pushing on the pivot point, that's a force, but it doesn't count as a torque because it's at the pivot point. So the radius is 0. So it's possible to have an external force, but no external torque. That would mean the translational momentum is changing, but the angular momentum is not. And the other way is also possible. It's possible to have external torque, but no external force. For instance, if I push down on one side and push up on the other side of the object, what's the total force? If I'm pushing down on one side and up on the other side with equal strength, yeah, total force would be 0. Those forces cancel out, down and up. But in terms of torque, if I'm pushing down on this side, which direction is the torque? Pushing down on this side, you can use the right-hand rule, right? Put your hand at the pivot point, stretch out towards where the force is located, curl your fingers in the direction of the force. That's a torque this way. So in this case, that would be towards the board. Whereas if you push up on this side, put your hand at the pivot point, stretch out towards the force, curl your fingers in the direction of the force, that's also a torque towards the board. So in this case, a downwards force on one side and an upwards force on the other side, as forces, they cancel out, but as torques, they combine. So this would be one way of getting an external torque without having external force. Two forces that cancel each other out as forces, but they're on opposite sides of the pivot point. So as torques, they combine. So it's possible to change the angular momentum without changing the translational momentum. Or of course, you could be doing both. If you just got an object floating in space and you apply an off-center force, that counts as an external force. And because it's off-center, it also counts as an external torque. So that's going to change the translational and rotational momentum. It's going to start spinning and start drifting away. Any questions on that so far?
What was the last part you said, the example you just gave about there being change in momentum and change in torque?
Yeah, if you apply a force and an external force and an external torque. For example, if you were to apply a force towards the center, that doesn't count as a torque. But if you apply an off-center force, like let's say you apply a force right here, that counts as a force because you're pushing on the object, and it counts as a torque because you're pushing on it off-center. You're going to make it start spinning. So as a force, it causes it to start translationally accelerating, or it causes it to translationally accelerate as long as the force lasts. And it also causes rotational acceleration as long as the torque lasts. So that means instead of just drifting away or spinning in place, it's going to spin as it drifts. So it's going to translationally move and rotationally spin.
Wait, so sorry. If you're pushing on the side of the fidget spinner,
Mhm.
why isn't that only not just torque? Because I feel like we've had examples in the past, like where that's how we start with
Mhm.
torque, like somebody walks on a Ferris,
Well,
or
if
like
you're pushing on
somebody.
it, if this is just truly just floating in space and you push on it, your push is going to make it start, uh, is going to cause translational acceleration because you are applying an external force. So that's going to cause its velocity to change. But it's also counting as a torque because it's off center. So you're going to cause its rotational velocity to change. That means it now has a change in translational velocity and a change in rotational velocity.
Okay, because the pivot point's not stationary.
Exactly. In fact, in order for the pivot point to be stationary, like if I'm holding this by the pivot point and I tap on it, I'm causing rotational change, but I'm not causing translational change because this is not the only force. I'm also holding it at the pivot point, so my other hand is exerting a force on the pivot point itself to hold it in place. So the force upwards from one hand and the force downwards from the other hand, and of course force of gravity as well, all cancel out. But only the force from one hand counts as a torque because the other hand is holding it by the pivot point. And if you're applying a force at the pivot point, the radius is 0, so you get no torque at all. Any questions on that so far?
Wait, why would the radius be 0 again?
Radius in this context, in the definition of torque, that torque is radius times force times sine theta. The r here, the radius, is the distance from the pivot point to where you're applying the force. So if you're holding an object by the pivot point, then any force you apply is going to be at radius 0. Like if I wiggle this around, I'm applying forces, but I'm not applying any torque because the force I'm applying is at the pivot point.
Oh, right. Okay. Thank you.
Mm-hmm. Any other questions on that so far? Then let's try actually applying some of this conservation of angular momentum stuff. Because we've taken a lot of looks at the conservation of translational momentum. The conservation of angular momentum can be different in some very important ways. One example would be if you, I mean, I think probably the most similar examples if you just got a couple of spinning objects and they bump into each other and now they're spinning at different rates. You could set up a very similar conservation of angular momentum chart where you've got object 1, object 2, total, and you're looking at initial angular momentum, change in angular momentum, final angular momentum. So that's going to be very similar to the translational momentum charts you've already seen, where maybe one of them is gaining momentum, the other one's losing momentum. But where this gets really interesting is where some of the objects are changing in other ways. For example, let's say you have, let's go with that example of stretching out your arms versus pulling your arms in. Let's say you are holding a couple of heavy weights. And you jump in a way that makes you start spinning. So you jump, and while you're pushing off the ground, how is it that you're able to start spinning in the first place as you push off the ground? So as you jump in the first place, why are you able to start spinning at all? You start at the beginning when you were just standing on the ground, you're not spinning. As soon as you jump, you start spinning. And how is that possible? What has to be happening to you in order to start spinning in the first place?
You have to give yourself rotational, like the torque, maybe.
Yeah, you've got to experience a torque, right? But you can't apply a torque to yourself. That torque has to come from an external source. So what other object are you in contact with that could be exerting a torque on your body?
The ground.
Yeah, the ground itself. as you jump off the ground, you're pushing on the ground, your foot is pushing on the ground, and Newton's third law says that the ground is also pushing on your foot. Newton's third law is the idea that forces come in pairs. If A exerts a force on B, then B exerts the same force on A in the opposite direction. Force from A on B and force from B on A are equal in magnitude but opposite in direction. So one of the forces is the opposite of the other. In this case, your foot is pushing on the floor in one direction as you jump. The floor is pushing on your foot in the other direction with the same strength. That's the equal and opposite reaction forces that Newton's third law is talking about. And that force from the floor on your foot is an external force. Since it's off center, it also counts as an external torque, so you start spinning. So you are now in the process of spinning, let's say slowly, you just get a little bit of torque. If you wanted to spin faster, like let's say you're currently in midair and you want to spin faster, is there anything you can push off against? Okay. Yeah, you could bring the weights in. You can't get a torque from the floor because you're no longer in contact with the floor. So if you are currently in midair, and spinning slowly, let's say you're currently spinning slowly, and that would be, by the right-hand rule, that would be an upwards angular velocity. If you pull your arms inwards, so you're now holding these masses closer to your chest, what has changed? What does that do? Right, we have decreased the moment of inertia. Because moment of inertia is going to be moment of inertia of your body, which is not changing very much because all you're doing is bringing in your arms, but also plus moment of inertia of those blocks. And by bringing the blocks closer in, you've decreased the moment of inertia quite a bit. In fact, we could even calculate that much. Moment of inertia of the blocks, since the block can be treated as just a single point, it's fairly small, it's fairly compact compared with the other distances. What would be the moment of inertia of one of those blocks? Yeah, mr squared. And since there's two of them, we'd have 2 times mr squared. We're not changing the mass, but we are changing the radius. By pulling the blocks in closer, we've changed the radius from maybe, let's say, 1 meter to maybe 1/4 of a meter. By changing the radius to 1/4 of what it was, but then we're squaring it, what do you get if you square 1/4? If the new radius is 1/4 times the old radius, but then we're squaring that, what happens when you square the 1/4? Yeah, you get 1/16. So that means the new moment of inertia of the blocks is only 1/16 as much of what it was. Your moment of inertia of the body is still staying pretty much the same because the body is not changing in this process. But this extra bit decreases significantly. Just the 1/4 is just an approximation. If I'm holding it out here, that's from like my chest, my center of mass out to my hand is about 1 meter, maybe a little bit less. If I pull it in real close though, that's much closer, maybe, and I'm just guessing here, about 1/4 of a meter. So if the distance shrinks to about 1/4 of what it was, then the new moment of inertia, because of the squared here, is going to be 1/16 of the old moment of inertia. And of course, that only applies to the moment of inertia of the blocks themselves. The moment of inertia of the person's body is not changing significantly. but this is still a large decrease in the total moment of inertia. And the total moment of inertia changing, this ties into the idea of angular momentum. So we've got the angular momentum here is initial moment of inertia times initial angular velocity. Moment of inertia here is final moment of inertia times final angular velocity. And since there's no torque in between, there's no contact with the ground between here and here, what should we assume about these angular momentums? If there's no external torque, what should we have to assume about angular momentum? Yeah, it's got to stay the same. The idea of conservation of angular momentum. If there's no external torque, then the total angular momentum of the system cannot change. So the initial angular momentum of u plus the blocks has to match the final angular momentum of u plus the blocks. But if we take a look at the changes that happened here, we started off with a large moment of inertia because you were holding the blocks outstretched, and that shrinks to a small moment of inertia. We also started with a fairly slow angular speed. So what has to happen to make sure these end up being the same value? Yeah, you've got a fast omega final. You're going from a large moment of inertia times a slow angular velocity and changing that to a small moment of inertia times a fast angular velocity. But the total product, the total angular momentum, is still the same. And this is generally the only way you can really change your angular speed without any contact with anything else. This is one of the biggest differences between translational motion versus rotational motion, that you can't change your translational motion without interacting with something else, but you can change your rotational speed by just tucking something in or extending something out. Yeah, did you have a question?
Yeah, when do we consider angular acceleration?
This would actually count as angular acceleration because as time passes, you have gone from this angular velocity to this different angular velocity. So you have experienced angular acceleration during this time, change in angular velocity divided by change in time. But note that this was all done without any torque at all from the ground. The ground did not exert any torque on body plus weights. There was no external torque at all. So we were able to angularly accelerate, rotationally accelerate without any external torque. And again, this is one of the biggest differences between translational motion versus rotational motion. Translational motion, you cannot accelerate without an external force because you can't change your mass. But rotational motion, you can change how fast you're spinning without any external torque because you can change your moment of inertia in one direction and your angular speed in the other direction. Increase this to decrease this, or decrease this to increase this, even though the total angular momentum does not change. Any other questions on that so far? And this has a wide variety of applications. Anytime you want something to change how fast it's spinning without being in contact with anything else, this is the way to do it. I think this is probably most visually obvious in various Olympic gymnastic type events. If you're like, this specific example shows up in figure skating all the time. You go into a spin with your arms outstretched, you tuck in your arms, you start spinning remarkably fast. Of course, you don't want to be spinning fast when you hit the ice again. So how do you slow down again? If you're spinning really fast, yeah?
Make your body as big as you can, kind of.
Yeah, you spread out as far as you can. So you stretch out your arms again, maybe put out one leg, and you now have a much larger moment of inertia. You're going back to a large moment of inertia, slow angular speed. So you tuck everything in real close, spin really fast, and then when it's time to hit the ground again, you spread out and you slow down again. Same thing in diving. If you're doing a high dive, Probably make that longer for safety. You jump off the board, stretched out, and you're in contact with the board. So you get a torque from the diving board as you jump off. But then how do you go into a spin? How do you start? I mean, you're spinning a little bit. How do you start spinning much faster as you're going off the high dive? What shape would you want to go into in order to speed up?
You would tuck your body in.
Like, yeah, tuck in into a sort of a cannonball type shape. So you tuck in, and by doing so, you've taken lots of your body's mass and brought it closer to the pivot point. In this case, the pivot point would just be your own center of mass. And since you are now much closer to the pivot point, you have a much smaller moment of inertia. Again, R has decreased. The average radius of all your mass has decreased. So you've gone from large moment of inertia, slow speed, to a small moment of inertia and a fast angular speed. So you're now spinning very fast. And again, of course, you don't want to be still spinning very fast when you hit the water. So you stretch out again. And if you time it just right, you can stretch out so that you slow down and hit the water going straight in, head first. And this is true for basically any sort of gymnastic or diving event involving changing how fast you're spinning while you're in midair. This is the way you do it. And this also has applications to all sorts of engineering as well. Like for instance, maneuvering rockets out in space. If you have a rocket that's out in space and you want to rotate it, like let's say you want to apply engine thrust, but you're not pointing in the right direction, so you'd like to rotate. One way to do that is to have smaller rocket jets on the sides. Like let's say you want to rotate this way. You just shoot some rocket fuel out of this exhaust vent and shoot some rocket fuel out of this exhaust vent. That applies torques this way and this way that cause your rocket to rotate. But that's expensive in terms of spending some of the limited amount of fuel. So another way to do that without necessarily spending any fuel at all is if you have reaction wheels. That is these enormous, well not enormous, but fairly massive wheels inside the rocket. By spinning those wheels and changing how fast they spin, you can to some extent control the orientation of the rocket, how fast it's spinning, how much it's spinning, based on how fast these wheels are spinning on the inside of the rocket. And that's nice because it doesn't require any fuel to do so. You've got to spend electrical energy in order to control the motors, but you can always make that back with solar panels. But it's a way to, in limited ways, control the rotation of the rocket without having to spend any fuel, just by messing around with how fast these wheels are spinning inside the rocket. Any other questions on that? All right, then we'll look into some more examples next time. Feel free to email me if you have any other questions, and I will see you then.
Thank you.
You're welcome.